All right, hope everybody had a good weekend. We are now in the fifth 6 weeks, so you've already got 6 weeks that is helping to determine what your average is going to be or what your semester grade is going to be. So, really be thinking long term now, because especially after spring break, which is only 3 weeks away, the year is going to start to go even faster. We're about to hit testing season, and all that good stuff is about to begin. But for this week and the next specifically, we won't have a Happy Minutes on Wednesday, and why is that? I'm going to be gone, so I'm still going to be on campus, but I won't be in the classroom. I'll leave something for you to work on with the substitute. That's why we'll probably go ahead and do some more Happy Minutes next week. But what's due tomorrow? Okay, the homework is due tomorrow. How's that going? Almost done? Okay. So the only thing really that I'm getting any questions on so far are the word problems, and I'm hoping by working on a word problem today that kind of gives you a little bit more insight into those, a little bit how to work them. But that's due tomorrow. Then on Friday is when you have your quiz over that material. But I didn't put any word problems on there. It's pretty much just the algebra. Find me this component form. Find me this magnitude, things like that. Okay. And then hopefully by the end of this week, we should be able to finish up this packet, which is just like a supplement to the lesson you are working your homework on, and get into the next lesson, which is dot products of vectors, and actually taking them a little further. But 2 weeks from today, you have your first what? Exam. So on Monday the 4th, okay, March 4th, that Monday right before spring break, you'll have your vectors exam. Hopefully we should finish everything up with vectors prior to that, and then go ahead and get into all the other concepts that we have to, like sequences and series and all that good stuff. Somebody knocked on the door. Okay, probably Alyssa. Hey, there we go. Okay. All right, I think. Oh, the only other thing, hopefully my remind text got out there last night. Okay, I was told on Friday that I have morning duty this week, and the schedule was changed without my knowledge, because my morning duty was originally scheduled for the last week before spring break, the 4th to the 8th. So I guess this works out better because there's no retakes to take from last week. I mean, nothing like that. If you do want to retake a Happy Minute, you have 1 week after the day it was given. So for this Happy Minute, if you want to retake it, you have until Monday of next week. Tomorrow's you'll have until Tuesday of next week, and just the same, it'll always be a week after the fact. But I do apologize about that. Hopefully that's not inconvenient for anybody. If you saw me in the cafeteria this morning, you saw how happy I was to be walking around, because that's exactly where I want to be. Okay, no sarcasm in that at all. But if you do need something or you have a question, just swing by right after school, and I'll do my best to help you out. But yeah, 7:45 to 8:05, I got to be in the cafeteria this week. So there we go. All right, I think that's all I have, unless anybody has any questions. Hey, Zach. Homework was given out on Friday. I believe there might still be some copies over here on the door. Okay. All right. Well, if we're going to get into some word problems, basically start applying what we've been practicing when it comes to vectors, well, we need to know about certain types of bearing, because these problems are going to be giving me angle measures starting from all kinds of different locations. So let's see, the direction of a vector can also be given as a bearing. Now there's two types of bearing. There's a quadrant bearing, and then there's a true bearing, and they are very different. A quadrant bearing, that uses this symbol, or phi, is a directional measurement between 0 and 90 degrees east or west of the north-south line. The quadrant bearing of vector v is shown is going to be 35 degrees east of south, and here's the notation for it. So typically you'll see it written like that. Quadrant bearing is bound to one quadrant. Okay, so it'll never make it past 90. If it does, you're going to have to either use a measurement from the horizontal or true bearing. Okay, but they could also just say it out 35 degrees east of south, so that'll give you the particular direction. Well, the way this works, the first letter is either going to be north or south, because you have to start on the positive or the negative y-axis, and then from there you're going to rotate left or right depending on if it's east or south. Okay, but again, you're going to be contained to just one quadrant. So in the example, vector v, that would be 35 degrees right there. 35 degrees east of south. Okay. If I were to give you one like this, if I said north 15 degrees west, what quadrant would that put me in? put me in 2. So the north means I have to start on the positive y-axis, and I'd have to rotate left because it says west. So yeah, so this little angle right here would be 15 degrees. Okay, that's quadrant bearing. You always begin rotating left or right off the y-axis, whether, bless you, the positive or the negative. Okay. Now, while that's quadrant bearing, we also have what's called a true bearing. That's a directional measurement where the angle is measured clockwise from north. So you start at true north, and you keep rotating clockwise until you need to stop. Okay, so this can go anywhere from 0, to 300, and really I would say 59, because 360 would be right at 0 again. Okay, true bearings are always given in 3 digits. So a direction measure that only has 2 digits clockwise from north would be written as a true bearing 0, 25 degrees. Okay, so it's the notation that we really want to get accustomed to. We'll know it's a quadrant bearing if it actually gives me north, south, east, west directions. But if your value is given a 0 in front of it, we have to believe that's true bearing. We always begin rotating clockwise from the positive y-axis. Or sometimes they'll just go ahead and say bearing. If they just say it has a bearing of, we always assume that that's going to be true bearing. Okay, so let's see here. The true bearing of V here is 145 degrees. Because see, to get this measure, we were south 35 degrees east. So if I'm going to measure from the positive y-axis, true north, well, that's 145 degrees. Okay. Now, there's also one other. If it's not given to you as a bearing, then you'll be given your angle measure with respect to the horizontal. So then you're going to be rotating off of what? If it says horizontal. The x-axis, the positive x-axis, and you'll rotate counterclockwise like we're accustomed to. All right, so we have these 2 types of bearing and basically how we worked with a lot of these trig problems. Okay, so let's go ahead and practice this. When using a ruler and a protractor, draw an arrow diagram for each quantity. I'm not interested in that. I don't even have the protractors anymore. I gave those back to Mr. Heinrich. He was needing them. So we're just going to go ahead and sketch these. All right. So the first example, north, south, east, west. It says vector A is 20 feet per second at a bearing of 0, 30 degrees. Okay. So we know the magnitude of vector A. It's got to be 20 feet per second. But what kind of bearing is this? Is it a quadrant bearing or a true bearing? It's a true bearing. How do I know that? There you go. Because there's no north, south, east, west, but it does give me a 0 in front of the 2-digit measure. So this is going to be in quadrant 1. So from north, I would just rotate 30 degrees. Bless you. So this would be vector A. Now, the quadrant bearing would actually be really similar to that. If I wanted to give it as a quadrant bearing, then I would go ahead and say north because we started on the positive. But then it would be 30 degrees what? East, because we had to rotate right. If I wanted to go ahead and say that it was with the horizontal, then it would be what? 60 degrees. Because remember, the quadrant's 90, right? So with the horizontal, that would form a 60. So see, it's really easy to find the other versions given one of them. It just depends on where you start rotating from. Okay, well, let's try another one. The next example, it says vector V, 75 pounds of force at 140 degrees to the horizontal. Okay, so this one specifically says to the horizontal. If it says that, you begin rotating from the x-axis. So what quadrant would this put me in? Okay, so from here over, let's say that's 140 degrees, then this would be vector V with respect to the horizontal. Okay. But let's go ahead and write these in terms of the other bearings as well. Let's go ahead and put this in a quadrant bearing. Let me do this in red. Okay, so I need from here to here. So would I have to start north or south? North, okay. And then we would definitely have to go west, so I'd have to end west. But how far west or left should I rotate? Yeah, 50. Because remember, this is 90. And for quadrant bearing, we begin rotating off the positive or negative y-axis. So this would be the exact same measure just as a quadrant bearing. Okay. Now what if I wanted it as a true bearing? I'd have to start from true north and go all the way around until I get there. So what would that be as a true bearing? Okay, 310. There you go. And that one already has the 3 digits, so there's no need to put the 0 in front of it. Okay. So see, it's really easy to get the other two no matter which one you're given. Is everybody okay with that? And what's important here, whatever problem you're working on, whatever version it gives you, quadrant bearing, true bearing, or with the horizontal, you want to make sure to give your answer the same way. You want to keep it consistent. Okay, and let's try this last one right here. So north, south, east, west. In fact, the one thing I'm having a lot of trouble with, I keep thinking, because my daughter, you know, she's in first grade and they're starting to teach her directions and everything, and they're teaching her a sentence to remember: north, south, east, west. Never eat soggy waffles. Did you guys ever hear that? Never eat sour watermelon. I just think it's funny how the words may change, but the idea remains the same as you get older. I just thought that was funny. The only way I'd eat soggy waffles is if they were soggy from maple syrup. Yum, yum, yum. Anyways, let's try this next example. Vector z, 30 miles per hour, so that would be the magnitude, at a bearing of south 60 degrees west. So it says bearing, so is that true or quadrant? This is quadrant, okay, because we are given actual directions. In fact, what quadrant would that be in? Yeah, 3. So because it starts with south, I want to begin rotating off the negative y-axis, and I'm going to go left or right. Left because it says west. So from here, I want to rotate 60 degrees. So that would be vector z, as we're calling it. Is everybody okay with the difference in the 3? Anybody have any questions on those? No? Okay. All right. Well, let's get into a problem. Now, there's kind of good and bad news today. The bad news is we're only going to be able to work one problem. Okay, the reason I'm going to go ahead and do that is I'm going to show you 2 different ways. You can do this graphically, as we were doing last week. You remember when we created a triangle using the triangle method? I'm going to show you how to do it that way, but I'm also going to go ahead and show you how to do it just algebraically with no graph using the formulas from the notes. Okay. Now, the method that I would encourage or suggest you use is going to be algebraically. But when this is done, if you're still, you know what, I like the graph, I'm going to go with the graph, as long as you're able to solve these problems. That's all I'm interested in. Okay. So I'm going to go ahead and do this graphically first. But there is also a lot of old friends that's going to be coming up if you choose to do it graphically. You're going to have to either use the law of sines and or the law of cosines to help you out here. So what was the law of sines? Sine of A, capital A over lowercase a, equals sine of capital B over little b, equals sine of capital C over little c. Remember, where the capital letter was the angle measure, the lowercase was the side length across from it. Now here's the difficult one. What was the law of cosines? And let's say I want to start it with side A. And remember, it doesn't matter what side you begin the formula with because the pattern was always the same. So what would I do with B and C? Okay, so I square them and add them. So B squared plus C squared. 2 times B times C times the cosine of angle A. You always end with the angle opposite the side you started the equation with. Okay. Now, in addition to that, you're going to also have to think about angles in geometry, like maybe vertical angles, the fact that the sum of 3 angles in a triangle is always what? 180. So there's a lot of previous information you're going to need to rely on if you want to do it graphically. Now you'll notice the way I'm kind of talking is I'm more favorable towards what? The algebra method, because it's way less work. But if you still think the graphing is the best, please feel free. I'm just trying to encourage you to go the other way. So let's take a look at the problem. In an orienteering competition, Tia walks north 50 degrees east. What kind of bearing is that? That's quadrant. Okay. So here's north, south, east, west. So we're going to do graphing first. So 50 degrees east. So that means this measure here is 50 degrees. We rotated right for 120 feet. So the distance that she walked is the magnitude of these vectors. So I've already got these two vectors set up. So while she rotated that distance, she went 120 feet. And then from there, she went due east 80 feet. Okay, so this is going to be 80 feet due east. Okay. Well, you remember what was the method we were using when we graphed these last week? We were trying to create what? A triangle. Now, it won't always happen like this, but sometimes the way the problem is set up, you'll notice the two sides of the triangle, they are already set up exactly how I need them to be. I've got the terminal of one connected what? To the, what do we call it? Starts with the initial of the other. Okay, so I don't have to move one of the vectors. Now, sometimes you will. It depends on how the problem is stated for you. So what we're trying to do here is find this. That would be the third side of the triangle. Remember, what do we call that? It starts with an R. That's the resultant. Okay, so I'm going to go ahead and call this vector R. If I'm doing it graphically, I always call that R. Okay. Well, here's the thing. There's two things I want to know about that vector R. I want to know his magnitude. So how far a distance is she standing right here? That's a horrible stick figure, but okay. After she walks these two distances, how far is she from her starting point? And in quadrant bearing, if I rotate from north over to this vector, how far a degree measure is that? Those are the two items we want. Okay, so let me take this back off right here. So now we have to get a little bit of creative when it comes to our diagram. Okay. Do we know any angles for sure? We have what? The 50? Okay, so how does that help me? Okay, we can use a transversal. Okay, so let's say that the transversal will be this one, these two lines intersected by this one here. Now I'm going to go ahead and put in one more, this one straight down. Think about if I put another coordinate grid with the origin right there at the terminal end of that 120 vector. Okay, so that what they're saying with the transversal, if this one's 50 right here, then this one has to be 50 as well. Okay. Now there's another way you can do that. You see how I created a triangle right here in the middle when I drew that horizontal line? Well, we know this one has got to be perpendicular. We know this one's got to be perpendicular. Does anybody know what the measure of these two angles have to be? They have to be 40, because remember we rotated 50 degrees, right? Okay. So if you're not liking the idea of the transversal, you know this is 40, that's 90, so that one still has to be 50. So see, you're going to have to use your knowledge of the diagrams and the angle measures from geometry to help you out here. So what's this full measure right here, this obtuse angle?
140.
It has to be 140, the 50 plus the 90. Okay. So 140 degrees. So let me go ahead and recreate this triangle down here, because that's a pretty busy picture. So we got this right here. We got this. Okay. Here's the resultant that we're looking for. Let me move that E. So we know this one was 120. We know this was 80. We know this measure was 140 degrees. Okay. Now, what first thing I'm looking for is the magnitude of R. So what am I going to be able to use? Law of sines or law of cosines? Why cosines? Why can't I use law of sines? What did we call that item you needed? Started with a P. You needed a pair. You needed a side length and the angle across from it. So I don't have enough yet to use the law of sines, but I can use the law of cosines. So I'm going to go ahead and say R squared equals, well, what do I do with the other two side lengths? Remember, we square them and then we add them. So 120 squared plus 80 squared, then what? Minus 2 times 120 times 80 times the cosine of 140, the angle measured across from the side length that we have. Okay. Solving this will give you the length or the magnitude that we're needing. Okay. So all I got to do is just take the square root of each side, right? Okay. So let me go over to the calculator. Let's type this in. Okay. So I'm going to come on over here. Oop, pay no attention to the man behind the curtain. Okay. So I'm going to go ahead and say control square root. Let's see. We got 120 squared plus 80 squared minus 2 times 120 times 80 times the cosine. And you just want to make sure that your calculator is in degrees because we're plugging in 140 degrees. Okay. So as soon as I push enter, how far is she from her starting position? What's the magnitude? 100 point what? That's exactly right. So let's say 188.4 feet. Remember, in this problem, the distance is the magnitude of the vectors. Okay. So I'm going to come on back over here. So this resultant is about 188.4 feet. Okay. So that is one answer. But now I need the other answer. I need my quadrant bearing for her location. So remember, this length here was 120. Okay. This represented the y-axis, and this was 50 degrees. So I need to rotate from the positive y and get there. So basically, I need that angle theta. Any ideas? Now I can use what aid? Law of sines. Because I have an angle and the side length across from it. We have a pair. So I'm going to say sine of what? So sine of 140 over the side length across from it, 188.4 equals, now we need sine of theta, we need this angle measure right here over 80. Is everybody okay with that? How do you solve a proportion? Cross multiply, divide, right? So if I were to do that, would everybody agree that sine of theta is going to equal 80 times the sine of 140 over 188.4? And how am I going to find theta? There's something I have to do to sine. I got to take his inverse. Okay. So let's see here. Theta is about, so let's go ahead and plug that in. Let me go ahead and first find out what that ratio is, because I'm going to use the exact value from the calculator. So I'm going to go ahead and say 80 times the sine of 140. Then I'm going to divide that by the actual distance that we got. So this is what sine of theta should equal, approximately. So I'm going to take the sine inverse of that ratio. So I'm getting about 15.8, let's say. 15.8 degrees, that's my theta. 15.8 degrees. So I guess my final answer is going to be north 15.8 degrees east. Or did I forget something? Because remember, where do we rotate from? From north, the positive y-axis. All we found was that this little angle right here is 15.8. So if I'm going to start from the positive y-axis, I have to add that to 50. There we go. So in fact, what would that be? 50 plus 15.8. 65.8 degrees northeast of where she originally started. There we go. That's if you like doing it graphically. Lots going in the diagram, law of sines, law of cosines, but maybe you like that. I don't know. Okay. Now, I want to show you the exact same problem but I want to do it using the formulas that we have in our notes, the one that your homework is based off of. This is how I would go ahead and take a look at the 2 word problems that are on your paper. Okay? Can they also be done graphically? Yes, if you want to. All right, so let's start all over again. Okay, now we want to remember these are the 2 answers I'm looking for. Okay, the magnitude, the distance that she is from her starting point, we got that to be 188.4 feet. And then we got her quadrant bearing to be north, what was it, 65.8 degrees east. This is what we're looking for. This is what we should get. Okay, but we're going to do everything geometrically. So there's a formula, a really important formula that we talked about last week that's going to be used here because you need the component form for all of these vectors. Let's say that the first distance she walks, that's vector u, and let's say the second distance she walks, that's vector v. Okay. The formula that I'm referring to is going to be this. The magnitude times cosine of theta, the magnitude times sine theta. Do you guys remember us looking at that last week? Okay. Remember, this will immediately give you the component form if you know theta and you know the magnitude. So in this case, the magnitude's what? How far Tia what? How far Tia walked, right? Okay. But there's just one catch. For this formula right here, you always need theta rotating counterclockwise from the positive x. That's the only theta it'll take. Okay. So you have to be careful. Let's say that for vector u, she has a magnitude of 120 feet because that's how far she walked, but cosine, I'm not putting in cosine of 50. Remember, this was 50 right here. What would it be from the positive x-axis? 40. Okay. That formula has to have theta from the positive x-axis, counterclockwise. Okay. So now what do you think the second part of that would be? Magnitude sine theta. Well, now we haven't got to the second vector yet. We're still on this same vector. So it's still going to be the same magnitude, but sine of 40 degrees. Okay. Now what I want to go ahead and do is just approximate these. All I'm doing is plugging into the formula. Is everybody okay? Okay. So let's see. 120 cosine of 40. I'm going to go ahead and take all of this off because we don't need it anymore. Oops. It's got the green on there. Let me go back, hit the arrow. Okay, hit the arrow again. So let's see. Document B. So I'm going to type in 120, and then I want cosine 40 degrees. It depends. Smart boards have not been very smart lately. Okay. Ever since he updated all that software, it's been a mess. But anyways, let's say 91.93. So that's 91.93. Okay. So 91.93, comma. Now I need 120 sine of 40. I'm going to come back over here, 120 sine of 40. Okay. 77.13. Okay. 77.13. So just to kind of tie it into what's happening graphically, she walked 120 feet, not degrees, 50 degrees northeast, right? So what we're saying here is in component form, she would be in exactly the same position if she walked 99.93 east and then 77.13 feet north. Remember, that's the A and B values. Those are the components that give you that vector, just like we were talking about last week. Okay. Now let's go ahead and set up V. So for the second one, she walked 80 feet due east. Okay. So think about it. If you're going like due east, how far of a rotation off the x-axis would that be? 0. Yeah. So you could set it up like this. We still got the magnitude, 80, times the cosine of 0, 80, times the sine of 0. Okay. I'll just do it down here. So what is the cosine of 0? Oh, it's not 0. It's 1. Think about the unit circle, okay? Here's the radius. So at 0, you have the ordered pair 1, 0. And remember, cosine is the x value, right? So 80 times 1 is 80. What's the sine of 0? 0. So 80 times 0 is 0. Okay. In fact, if it's in due north, due east, if it's going exactly one of those 4 directions, you know one of your values, either A or B, has to be 0. So you don't necessarily have to use the formula on that one. Now, you remember how graphically we got this resultant R? Okay. Well, now that I have the component form of the other 2 vectors, R is just going to be U plus V. So what is 91.93 plus 80? It's 100 and something. 171.93, right? Now add the Y values. 77.13 plus 0. 77.13. This is the component form of the R we're looking for, that resultant. This is the A, and this is the B. How do I find the magnitude of a vector in component form? You square them, you add them, and this is all below a square root. So the square root of A squared plus B squared, remember that's the A and B. So 171.93 squared plus 77.13 squared. What do you think that's going to come out to be? What was the magnitude of the resultant we got graphically? 188.4, right? So let's see. Parentheses, and I'm just going to go ahead and use the decimal values here. 91 point, oh, what am I talking about? Sorry. 171.93. Gummit. There we go. Let's see if I can do it now. Squared. Then plus, there we go, 77.13 squared. The exact distance she should be. The magnitude of that vector we just found is the distance we found graphically, 188.4. Okay. Now, that's not the end. We still got to find the quadrant bearing, right? So we mentioned this other formula last week. Was there some tiny little formula that would give me the measure of theta that I was looking for? Starts with a T. The what? Now, not the Pythagorean theorem, but it's the same page where you had this formula right here that we just used. Tangent of theta equals what? B over A. Okay. Well, you've got the component form of the resultant, so there's your A and B right there. Okay. So I'm just going to go ahead and plug that in. But just like this formula, where we had to put in 40 degrees because it rotates from the positive x-axis, this theta will rotate from the positive x-axis as well. Okay. So let's keep that in mind when I plug those in. So I'm going to go ahead. Now, in order to find theta, I got to do tangent what? Tangent inverse. Control divide. Well, B was a 77.13 over. The A value was the 171.93. And there we go. But wait a minute. Didn't we get a 65.8? Remember, we're rotating from where? There we go. So we rotated and got 24.2 degrees. But for the quadrant bearing, we should be rotating from the y-axis. So what do I need to do with this one? I need to subtract it from 90. So I'm going to go ahead and say 90 minus, okay, let me highlight that previous one. Oh, 65.8. The exact answer we got the other way. So north, 65.8 degrees east. Okay. And I mean, just look at how much less work it took to get the same answer. Okay. But I don't know. Is there anybody out there who's still like, you know what? I like that graphing method. There are a few folks. Hey, if you like it, please feel free to use it. I think the algebraic is going to be so much faster. Okay. So here is what I would like you to do, because there's no way we're going to get through another one today. We're going to go ahead and stop. Okay. So the next problem gives us this right here. While playing a golf video game, Anna hits a ball 35 degrees above the horizontal. So that means what? Rotating from the positive x-axis, yes. At a speed of 40 miles per hour with a 5-mile-per-hour wind blowing is shown. Find the resulting speed and direction of the ball. Okay. Well, you'll notice in the diagram here, it's telling me that the wind is blowing due what? East or west? East. So if I say that W is the wind vector, well, can anybody tell me immediately what that component form has to be? 5-0. So on the last problem, we were looking at the length of the vector, okay, as the magnitude. Here, we're just saying it's speed. But if it helps you to think of it as in terms of length when doing your diagram, doesn't change anything. But if you want to go ahead and plug it in, how far would I have had to have rotated off the x-axis to go due east? I wouldn't have rotated at all, right? Wouldn't it have been 0? So that would be 5 cosine 0, and then that would have been 5 sine 0, and you're still going to get the same thing. Okay. In fact, let's say the other vector, the path of the ball. Okay. I'll go ahead and get it started for you. What's the magnitude or speed of the ball? Okay. She hit it 40 miles per hour. So I'm going to say 40 cosine what? 35. Now, wait a minute. Why am I able to use the degree measure it gives me in this problem, but on the last one I couldn't? There you go. Remember, this formula will only take theta from the positive x-axis, going counterclockwise. That's why we had to change it. This one already provided me that. What would the b or y value be? 40 sine of 35 degrees. Now, if I want the resultant, okay, that third side that I'm trying to find, what am I going to do with b and w? Just add them up. Okay, so right there, I've actually already done the majority of the work for you. Okay, but if you want to do it graphically, please feel free. Tomorrow we'll come back and we'll start here, and we will see how everybody did. Okay. Questions? Anything about today confusing anybody?
Why did we do that? You did like
Now, we took the inverse at the end with tangent because we still need to know what direction the ball is actually going.
Oh, okay.
Okay. So in this case, we want our final answer of the degrees to be from the positive x-axis. Like on the previous problem, we wanted the quadrant bearing.
Oh, okay.
Okay. There we go. Okay, well, let me go ahead and get this all out of here. Okay. Oh, that's not what I